Hello, and welcome once again to my channel. In this video, I'll be showing you how to model a robotic arm from scratch, just as I promised in the last video. As I mentioned previously, our goal is to build the BCN 3D MuJoCo robot, and by the end of this tutorial, you'll have a robot that looks just like the one I'm about to show you. This is the exact robot we'll be modeling. So let's get started. Just as in every project, I've structured this mini project into clear sections. First, we'll deal with the meshes that form the robot for visualization. I've carefully prepared all the required assets for this. To make things organized and easy to follow, the robot is divided into the following sections. The base, which is the main platform, including the plastic base. The hip, with its motor and attachments. The hind arm, forearm, wrist, the hand, and finally the gripper, which we created in the last video. If you missed that, check out the link above. All the 3D models for each section are contained within organized directories. As in previous videos on modular designs, we'll use the same pattern here. Each part is modeled independently before we bring them all together into a single assembled file. This separation also allows you to work with and understand each section individually before assembling the whole robot. Now, let's look at the general assets, particularly the XML file that defines the materials. This file manages the appearances, colors, and more. We'll start with these materials. I'll first define some defaults, something I've explained and demonstrated in my earlier tutorials, so make sure you're familiar with that process. Within the assets, I'll define the materials we'll use. I'll also add a texture to give our environment background color. For example, if we add this texture, you'll see a background that transitions from light blue to white. Remove it, and we go back to a black background. This really helps set the environment as we work. I'll set up different colors and materials for the various sections of the robot. Nothing too complex here, and you'll see this all in action shortly. Once those are defined, the next step involves modeling the base. To illustrate modeling each section, I'll demonstrate the process using just one as an example. The methodology is the same across all sections. It's mainly the specific meshes and their positions that change. It's important to have a properly arranged 3D model so you can extract accurate positions for assembly. If you haven't already, please consider subscribing. It really helps support the channel and motivates me to create more content like this. Let's begin with the base modeling itself, since this is the foundation for every other part. Right now in our project file, you can see the background is dark. There's nothing visualized yet. The first thing we need to do is specify where our mesh files are located by setting the mesh directory. Then, we'll include our materials XML file, which not only sets up appearances, but also brings in our background. After reloading, you'll notice we now have a background in place, making the scene much easier to work with. Next, I'll create some defaults and a visual class that will be applied to all our meshes. This includes specifying their relative positions, an important step for maintaining consistency as we import each mesh. Let's pause here for a moment. Before jumping further into the defaults, let's create our asset definitions and import all the relevant mesh files for the base. Now, we move ahead and create the world body, then add a child body within it, which we'll call base. At this stage, if we reload the scene, there still won't be anything visible. That's because we haven't added any geometries yet. So, let's begin by adding the primary piece, which is the plastic visual, forming the main base of the robot. I'll comment out the other parts for now and focus on this one so we can see progress more clearly. Now that our plastic visual is in, let's enable the frame body visualization. To make assembly and modeling easier, it's vital to follow a precise pattern. Always arrange the rotation axis, or the reference axis, at the start of the rotation axis, for example, just behind the circle here at the base. I want the z-axis pointing up along the rotation axis. This makes it much easier to add and align all the other robot sections later on. It's important, especially when modeling for simulation or future control, to have the rotation axis for each joint be the z-axis, aligning with the Denovet, Hartenberg, DH, convention. This makes it straightforward to later implement mathematical models, kinematic equations, or controllers. To achieve this, we apply a relative transformation, assuring the frame is placed exactly at the start of the intended rotation axis. It's crucial to always align the axes in terms of angle before position because MuJoCo considers angular alignment before translational placement. If you do them out of order, your positions may be off. Once the axis is rotated correctly, we then move the object, not the axis itself, to the center, which involves shifting it along the negative x and z directions. After tweaking these values and reloading, you'll see the base exactly where we want it, aligned perfectly for future assembly. By aligning the axes like this in every section, integrating the various robot parts later becomes much easier. For example, when it's time to add the hip, as long as its reference axis is positioned the same way, you can place it at the precise distance, the length of the arm or connecting part, from the base. Because all these STL files were generated from the same assembly, their references already coincide, so one transformation per part is enough. Now that the alignment is correct, I'll add all bodies and reload. There, you see the whole base placed just as intended. This approach is repeated for the remaining sections: the hip, hind arm, forearm, wrist, hand, and gripper. Each file follows this same pattern. Define the mesh, set the alignment, add the relevant parts, and check the visualization. Now let's assemble individual sections of the robot together into one larger model. When assembling the entire robot, we use a hierarchical or tree structure, so each body contains the next as a child. So, for example, the base contains the hip, which contains the hind arm, and so forth, down to the gripper. This approach keeps the movement of each section properly referenced to its parent. A key principle if you want your robot motion and simulation to be physically realistic and mathematically accurate. When working with the full assembly, I also bring in a patterned floor and gradient sky to improve the visualization. By importing assets, textures, and backgrounds, you make the workspace more engaging and easy to interpret. Once all parts are added, base, hip, hind arm, forearm, wrist, hand, and gripper, add joints to connect them, typically allowing rotation about the z-axis. By default, MuJoCo sets this to the z-axis, which aligns perfectly with the axis alignment pattern I chose earlier, but if your model needs otherwise, specify the axis directly. If your early model collapses or sinks, that's likely because collisions aren't defined yet. For this basic demonstration, I omitted collision bodies to keep things simple, but you can always add them later, just as I showed in my previous video. Adding actuators is the next step. These are your virtual motors. For each joint, assign an actuator, typically position controlled via PID parameters, KP and KD. High damping is used initially to reduce oscillations, and you can tune these later for your particular setup. While this is not how you'd control a real robot in hardware, it's great for simulation and visualization. With all actuators set, reload the scene and test each joint's movement. You'll see that the robot responds smoothly with minimal oscillations, thanks to the damping. This demonstration setup lets you easily experiment with new designs, control schemes, and more. The complete robot model and all related code are available in my GitHub repository. Check the description below. In the next video, we'll take things further and explore even more interesting modeling topics. If you haven't already, please subscribe for more in-depth tutorials. Thanks so much for watching, and see you in the next video.